the CLAPEYRON equation. In calculating thermodynamic properties such as enthalpy or entropy, thermodynamic properties such as enthalpy or entropy, in terms of other properties that can be measured, the calculation fall into two broad categories. The first one is differences in properties between two different phases. In properties between two different phases. And change within a single homogeneous phase. Or change is within a single homogeneous phase. In this section, we focus on the first of these categories, that of different phases. This chapter, the different phases. Let us assume that two phases are liquid and vapor. But we will see that the result applies to other differences as well. Consider a Carnot cycle heat engine. Operating across a small temperature difference. Differences between reservoir at T and T minus delta T. The corresponding saturation pressure at P and P minus delta P. The Carnot cycle operates within 4 steady state devices. In the high temperature heat process, the working fluid changes from saturated liquid at point 1 to saturated vapor at point 2 as shown in the picture here. Let me show on the next page. QH equals to TSFG and QL T minus delta T. This is QH and QL T minus delta T SFG. This process is real process, but for the Carnot cycle SFG for reversible heat transfer. So that we have W net QH minus QL delta T SFG. From the figure, we can calculate that W minus V dP or overall for the 4 process in the cycle. W net V dP plus 0 minus V dP. The two work will be down between 2 and 3 and 1 and 4 processes here. The constant pressure process in turbine and compressor are 0, we can write this relation. P minus delta P minus P V plus P4 V equals to delta P The smaller the delta P, the better the approximation. Now comparing these equations with the equation W net QH minus QL W net, with comparing these two relations, we can write the appropriate relations. Delta TSFG. So with make an equality, we can write delta T SFG delta P delta P on delta T equals to SFG V. In this limit, as delta T tends to 0, V3 equals to and V4 V1 Vf. Limitation delta P on delta T tends to 0 up to dP saturate on dt we make an equality and also apply this relation to these two ones. We can write the QH this relation for SFG on VFG. And now QH equals to FG TS dP saturate on dt sfg efg hfg tvfg. Clapeyron equation. This is very simple relation and yet an extremely powerful one. We can experimentally determine the left-hand side of equation, which is the slope of the vapor pressure as a function of temperature. We can also measure the specific volume of saturated vapor and saturated liquid at a given temperature. So with Clapeyron equation, Tp saturate on dt sfg on vfg hfg on tvfg. With this equation, we can simple relation and yet extremely powerful. We can experimentally determine the left-hand side of the equation, which is the slope of vapor pressure as a function of temperature. We can determine the slope of vapor pressure as a function of temperature. We can also measure the specific volume of saturated vapor. And saturated liquid at a given temperature. Which means that the enthalpy change and the entropy change of the vaporization can both be calculated. Enthalpy change and entropy change. Can be calculated. This establishes the means to cross from one phase to another in first or second law of calculation, which was the goal of this development. We could proceed along the same lines for the change of phase from solid to liquid or from solid to vapor. Solid to liquid or solid to vapor. We could proceed along the same line for change of phase from solid to liquid or solid to vapor or liquid. In each case, the result is the CLAPEYRON equations, in which the appropriate saturation pressure, specific volume, entropy change, and enthalpy change are involved. CLAPEYRON equations. We know that VF minus VI is typically a very small number. In this case, I for solid and F for liquid. Such that the slope of the function is very steep. Slope steep. In the case of water, VIF is a negative number. In the case of water, VIF negative, which is highly unusual, and the slope of the fusion line is not only steep, it is also negative. For sublimation, the change from solid I directly to vapor G the CLAPEYRON equation has the value dt a special case of the CLAPEYRON equation involving the vapor phase occurs at low temperatures when the saturation pressure becomes very small. The specific volume Vg is then not only much larger than the of the condensate phase or solid in the recent equations for the CLAPEYRON equation, but it also closely represents the ideal gas equation of the state. So the special case is involving the vapor phase occurring at low temperature when the saturation process becomes very small. Saturation pressure the specific volume Vg is not only much larger than the conduct surface, but also is also closely represented by the ideal gas equation state. Equation of state. dP saturate on dt, for this case HFG on T BFG, HFG P saturate on RT2, VFG equals to RT on P saturate. At low temperature, not near the critical temperature, HFG does not change very much higher than the temperature. If it is assumed to be constant, can be rearranged and be integrated over a range of temperature to calculate the saturation pressure at a temperature at which is not now. So we can write at low temperature but near critical temperature. HFG does not change very much. So we have this relation. dP saturate on dt, HFG P saturate on RT2. We can make an integration. dP saturate HFG P saturate dt. At low temperature, HFG is constant, and we can calculate delta P. For example, RT2 and HFG are constant. Mathematical relation for a homogeneous phase is the next section.